interesting artwork is working with School of Dance Augmented Reality. So working with different disciplines is always interesting because there are a lot of different things. It's not really concerned about performance, but how the usability is. I know Dr. Buchholm will tell me a lot about the software has to be, very user friendly. So without any further ado, then I will let Mike to talk about his thesis work, which is a very interesting piece of research work. Okay.
Dr. Biden, thanks for the introduction. So, like I said, I'm going to talk about my thesis work, which is something I've been focusing on for the past 2 years. And from starting with working with Calibration with the School of Music and Dance, we've encountered some problems and picked some fundamental research to really go into and try to make the system that we designed for them better. And so my thesis topic is on the performance evaluation of full 3D calibration methods in spatial augmented reality. So I'm going to start by giving you a little bit of background. I know you guys heard it during the proposal, but just to refresh your memory about why we want to combine the fields of art and engineering and what augmented reality is as opposed to virtual reality and exactly what is spatial augmented reality with projection. Then I'm going to identify the calibration problem in our dance application that we've worked with the Weir College of Music and Dance, and then give you a little bit of background about the Kinect RGBD sensor and how it might help us with our calibration problem. Then I'm going to talk about two different calibration methods. One, which is sort of the accepted way, it's been around for about 10 years, and the other, which is I'll be implementing the RGBD sensor to calibrate a projector. And I'm going to go into the comparison of these two methods and then talk about, we'll have a discussion about the results and I'll discuss the future work. So there's been a lot of interest in combining the fields of art and engineering. A lot of projects are being developed exactly for the purpose to help artists use new technology in their projects and how to make it easier for them to use hardware and programming in a way they can understand easily. So some of the big projects that have been developed is a whole new processing language or programming language called processing, where somebody who has no previous programming experience can just pick it up and learn it within a matter of days. Open Frameworks, which is a wrapper library for OpenGL that makes it easier to create visual displays. And finally, Arduino microcontroller platform, which everybody already knows about. We use it here, and it makes it easier for people to integrate hardware into their projects. And like in this case, LilyPad has been used to incorporate in a textile. So, augmented reality is different than virtual reality, because I hear that question a lot. So what's the difference? With virtual reality, the user is immersed in a virtual environment completely, whereas with augmented reality, virtual elements are superimposed on the real space. So, for example, an augmented reality display could enhance the user's view of the environment that he's in. So there's been mobile applications being developed where you can look through your phone's video screen and it could give you helpful annotations about your surroundings. So the mobile application is just one of the display techniques with augmented reality. So it requires either some sort of handheld device with a video camera or sensors that you can use to see through the camera view with digital elements superimposed upon it. And people have been using it for applications in gaming and also navigation. Another display technique for augmented reality is the head-mounted displays, and that's sort of similar to what a pilot would use with his heads-up display, which gives them important information in real time about the battle space superimposed upon its view. So the technology that we're most interested in is the spatial displays. So what makes spatial displays different from the other two is you don't need any sort of hardware or equipment on your person to be able to experience the effects of it. So it's nice because it encourages collaboration from the people who are watching the display, and apart from those, it can be used by multiple people at the same time, since those things are very personal, like a helmet that you wear on your head. So one way that we're making the connection to art from augmented reality is that a lot of artists in the recent years have been interested in this sort of new art form called projection mapping, where they take projected elements and overlay spaces with projection to create special effects or in the use of advertising. But the drawback with this case is that it being an art form versus a science, these projections are actually manually overlaid, so the cameras and projectors have to be adjusted and the images have to be scaled properly. So the work that I'm presenting handles this calibration process or alignment automatically. So in 2010, we've worked with the Boyer College of Music and Dance. After talking to them about augmented reality and knowing that they're interested in projection mapping, because they've heard of the art form, they were kind of excited about the idea of incorporating projection mapping into their dance performances in real time. So from that, we've kind of settled on the idea of having the dancers or performers holding some kind of projective plane that they can move around through the space with a video image or some kind of special effect projected on the plane that they're holding, which we can track and reproject onto in real time. So the kind of like component layout with this was a camera would be calibrated with a projector. So a relationship from the camera view was made with the relationship with the image in the projector, and while the camera was tracking this projective panel, we're then able to process the tracking information and work the coordinate system in a way that when the projector projects out the image, it looks as if the image is stuck to the board as they move around through the space. So let me show you a video of what supposed to be a YouTube video embedded in this.
You have player problems in a machine.
I guess. All right. Anyway, but so what happened was, like I said, they were all holding the projective panels and they moved around through the space with special effects following their bodies and the plane that they're projecting on. And from that, there was we encountered some problems, like the tracking was done at a delay, and then also as they moved through the space, away from the center, the projection would start straying off of the projective panel. So the calibration wasn't ideal. So from those problems that we experienced through our collaboration with the dance school, we wanted to focus on some of them and try to see if we can improve it for the next iteration of the project. So the problem that we decided to focus on in that case was the projector camera calibration. So having a good calibration would allow us to perfectly overlay objects in the space. So what exactly is calibration? So you can think of a projector and a camera, they both have this kind of cone of view. So when you use a wide angle lens, you can see more. When you use like a fisheye lens, you see less. So the projector has a cone of view and the camera has a cone of view. Since the projector and the camera are in two different places, the projector sees things differently than the projector would see them. So our goal is to take these two views and come up with a way to transform one image into the other image to make it as if these two cones of view were actually at the same place. So how do you take the information that you get through the camera, transform it in a way that it looks as if the projector is getting it? So essentially taking the camera lens and putting it inside the projector's lens. So with our work with the dance school, we used a 2D planar calibration, for which we basically made a relationship between just the two images. But that's not the perfect way to do it. Ideally, what should be done is making a complete relationship between one lens's cone of view and the other lens's cone of view, rather than just the images, because the images are a product of those intrinsics from the projector and camera. So in my thesis work, I've examined two ways of how to do that. One way was the kind of popular way, and one way that we proposed with the 3D sensor. So the 3D sensor that I'm using, this is the first 3D sensor that actually became commercially available, the Xbox Kinect. So it can provide full 3D depth information of objects in its field of view at 30 frames per second and at a resolution of 640 by 480 and 640 in depth. And you can see in some of these images that there's a black shadow behind objects. So the black shadow is due to occlusion because the way it works is actually projects infrared light. So things that are behind that projected light don't have a depth signature. So the raw picture that we get from the Kinect is sort of like this. So things that are further in are dark gray, and things that are further out are light gray, with the white parts being undefined areas. So to make a really usable snapshot of the space, we need to fill in these undefined areas. And the way we've done that is using an in-paint technique in OpenGL. And what happens is it actually gets the nearest neighbor pixels and fills them in with edge information from the other pixel. So using some of the open source software and drivers for the Kinect, you can actually do tracking on things in a depth image, and then use that information to then project overlays on top of it once you've made a good transformation. So I had some videos over here on YouTube of things that we did in the past. I showed you them during the proposal presentation. Here's a couple updates, but basically what we've done is we've used several open source drivers from which you just get basically raw point data like this, and then you have to do actually point cloud analysis to do tracking within that information. And then the closed source driver, actually by the company that developed the Kinect, can give us access to the skeleton. So for the thesis, we wanted to stay away from using this and actually use the raw data. So before I get into talking about the calibration methods, I want to give you a short introduction about how cameras and projectors work and what happens in the camera. So this is the camera image. So when you take a picture, this pixel frame is what you see as a result of taking the picture. So, and what happens is when you take a picture of an object in real space, in the world frame, that object gets projected through the pixel frame to the camera center. So, and this projection to the camera center is governed by this idea of focal length. So when you hear about a 35mm camera, that basically means that the image frame is 35mm away from the focus point of the lens. So the longer the focus distance, for example, this is F, the focus distance from the center of perspective projection to the image plane. So if the focal length is shorter, you ever have a wider field of view. Since you can see that points from out here will be able to get projected to the center. If your focal distance is long, you have a narrow field of view, kind of like when you see a 300mm lens in those like telephoto cameras. So another concept, so the way that this transformation actually works mathematically is you have a three-dimensional pixel in a three-dimensional object in the world frame, which is XYZ coordinates in relation to the camera, and then you have two-dimensional pixel positions in the image plane. So the projection happens through the use of this matrix of intrinsic parameters, which are just part of the camera itself. So depending on the camera's lens, you might have different focal parameters and principal point, and the rotation and translation matrix of the camera in relation to the objects that it's taking a picture of. So once you take a three-dimensional point, multiply it by the projection matrix, you're going to get back your two-dimensional pixel point. And this one important thing to note is that for the projector, all this happens in reverse. So instead of having a three-dimensional point, it takes a two-dimensional point from its image, which is basically just a desktop, and it takes it out and projects it to 3D. So we can take this matrix and actually do an inverse and do the reverse thing with it. But what the thing is, since this only has x and y in a scalar, we won't actually get the 3D point back. We'll get the projected ray where the 3D point could be. So anywhere along this ray. So the next thing I want to talk about is the 2D planar transformation, or homography, or perspective transformation, all the same thing. And what it is a perspective mapping from one plane to a different plane. So having 4 points on 2 planes, 4 corresponding points on 2 planes, you can get 8 equations for their x and y and figure out 8 of these 9 parameters in the homography transformation. The third, or the 9th one, is undefined into scale. So when you take 4 points on one image, 4 points on the other image, once you get this back, you can then take any point on one of the images, multiply it by the homography matrix, and figure out the corresponding point on the other image. So the example of that is, in this case, this calibration pattern is, since this chessboard is known, the checkers are known to be square. So taking 4 points out of these 48, or for a better result, you can take all 48. You can figure out the perspective mapping between this image and a plane. So multiplying this image by the homography that we determined, we can then recover the actual face of this calibration pattern. The same in this case with the building. When the building can be assumed as a plane, if you take 4 points on this, you can then recover what it would look like from the front. So, knowing these 2 concepts, I can start talking about the 2 calibration methods that I've used. And the first would be our RGBD sensor-based calibration. So in this case, what you have to do, like I said, with when you take an inverse of a projection, you get an undefined ray where your three-dimensional point would be. So in order to figure out the projector's intrinsics, we need to figure out the actual x, y, z coordinates of those points that the projector projects. So to do that, when we heard about the 3D sensor, it became really appealing because you can tell the depth of any point in the space. So what we have to do in this case is calibrate the RGB camera and the depth camera on the sensor, figure out the corresponding mapping between the 2 images, and then use those 2 images to look up the depths of the points. So once we can figure out the 3D locations of the corners, we can calibrate the projector. With the ray plane intersection method, what happens is it doesn't use a depth sensor, it just uses a regular camera. But, so in order to figure out the XYZ locations of all the points, we need to take those rays that the projector is projecting and basically terminate them at a known plane. So if we have a known plane in the camera's image, we can figure out where those rays from the projector's image will terminate on the plane and figure out their XYZ locations on that plane. So with the RGBD sensor, there's 2 images. There's a regular camera image, and there's a depth camera image, like I showed you with the points. So since those are basically just 2 different cameras, they have different parameters, they have different focal lengths, and not only that, they're also separated by some distance on the sensor itself, since they're 2 different cameras. So when you take those 2 images and put them on top of each other, you get something that looks like this. So the depth image doesn't perfectly align with the RGB image. So what we're interested in is taking a point from the color image and looking up its depth. So if we tried to do that here, we wouldn't get the depth of the appropriate point. So what we're interested in actually is getting those 2 to match. So there's 2 different ways to do that. There's one way that I already explained, and that's the homography, taking a mapping from one image to the other. And the other way is stereo calibration, from which is basically we have to figure out the intrinsics of both cameras and their actual physical relationship to each other, as far as like how many meters they're separated and how many angles, or which ways they are looking at. So the stereo calibration is theoretically supposed to be much more accurate.
I hate to kind of interrupt, but remind me where the Kinect fits into all this. So Kinect measures depth.
Yeah.
And how do they do that?
It projects out rays of infrared points that cover the space.
Okay, so it's infrared.
Then there's an
stereography
infrared
or
camera
something.
on there.
It's using multiple infrared beams?
Yeah, the infrared beams are refracted through a screen.
Right.
So the entire space is covered in dots, and then the infrared camera sees the dots, and depending on between its space, between all the dots, the GPU on it calculates the depth.
Okay, and explain again how your problem is different from that.
What do you mean?
So, well, you're talking about these different techniques for calibration,
Right.
but the Kinect kind of solves this problem in one particular way.
Yeah, so the Kinect can actually tell us the depth of things because it's a depth sensor.
Right.
But the way people have been doing it with cameras is more complex. I'm going to talk about the camera way after this way, but essentially what it does is, since the projector projects rays through the image plane.
So Kinect doesn't have the problem of calibrating image with depth, does it?
It does. That's what I'm about to talk about. Since the image doesn't, the depth image doesn't align with the camera image.
So which technique does the Kinect use of these? Does it use one of these?
It doesn't.
Okay, you're going to talk about what it uses next, or
I'm going to talk about how I'm going to solve that problem. Because it has two images. It has a depth image and a color image.
Previous, like,
But-
just this.
yeah, I kind of got lost
just,
here
just
about.
here, not just here.
What?
So the Kinect solves these problems.
That's
The way that, well, we want to use the Kinect to solve these problems. Since,
The Kinect currently doesn't solve these problems.
right, nobody's applied it.
So the Kinect, when in its consumer mode, is just using the infrared and measuring depth.
Yeah.
And then it has a camera to measure motion.
The camera on there doesn't, it's not corresponding, well, this is corresponding with the depth camera, but nobody's applied it in both senses yet.
Yeah, but the Kinect does object recognition or pattern movement.
Yeah,
So it's doing that using both the depth and the camera,
right.
but it doesn't have this alignment. They're not so worried about this alignment problem.
Right, because in the case of playing the game, it's not really a big issue.
That's what I was trying to get at, is that, so the Kinect doesn't really have to deal with these problems.
Right.
doesn't have another one projector there.
Right.
Because we wanted to use it as like an accurate measuring tool.
Yeah, no, I get that. Just was trying to understand kind of where state of the art is, so to speak. Okay.
But there is other 3D sensors that are coming out that I'm sure are solving these problems. But yeah, so we want to figure out a way to take these images and put them on top of each other. So to do that, we have to get 4 points. Well, to do that with the homography way, we have to get 4 corresponding points in one image and the other. And since one is a color camera and the other is a depth camera, they don't see things the same way. So we want to use the calibration pattern, the chessboard calibration pattern, because it's using a lot of algorithms. It makes things easy. So we're trying to figure out a way to get the Kinect to see the calibration pattern. So one way to do that is using a plexiglass sheet with filled-in squares. That way the infrared shines through them, and we can see the checkerboard pattern. This way doesn't work all the time. It's when the screen gets smudged or something like that. So what we've done is we've created this raised chessboard. So we have white cardboard in the back with the chessboard raised by some direction, some way. So this can be seen in the color camera, and the corners can be detected, and this can be seen in the depth camera, and the corners can be detected, because the chessboard is by some distance away from the background. So having these two images and being able to see the calibration pattern in both images, we can detect these points and start to make correspondences. So without a correspondence, when you take that chessboard pattern in both images and take an average of all the points, we can, this is for about 100 iterations, and the blue is the checkerboard corners in the depth image, and the red is the checkerboard corners in the RGB image. So you can see that there's about like a 30 pixel separation between the two images. And also you can see, this is going to become important later on, is that the depth image has a bigger variance. These are kind of like in a much nicer neighborhood. And you can see that with the standard deviation, the depth image is about like 1.5 pixel, when the RGB image, the deviation is less than 1 pixel. So, like I said, with the homography, you just take 4 points on one image and 4 corresponding points on the other image. You get the homography transformation, and you can take the other and transform it into this one. And this is an example of some of the homographies that we got. So this is what the matrix should look like. And taking those, this is again is the two corners overlaid on top of each other. So without any calibration, it looks like the chessboard corners in the color image don't align with the chessboard corners in the depth image. So, but once you do get them to align, you can basically just take a RGB pixel in the color image and look up its depth from the depth image, because you have a corresponding pixel. So the other way to calibrate the two-camera system is using a stereo calibration, which a lot of people do, especially for 3D reconstruction. So when you have a stereo camera system set up, you can tell the depth of things in the space. But we're not using it for that in that case. We just want to basically figure out the relationship of one view to the other view. So this is a much more involved process than with the homography. With the homography, you only need one snapshot of the calibration pattern, and you can figure out the mapping. But in this case, you need to take a bunch of snapshots with each camera to figure out the camera's intrinsics. So you need to figure out the focal depth of both the RGB and depth camera. And the way that's done is the several snapshots of the calibration pattern are taken, and then the snapshots are compared from one to the next with homographies. And from decomposing those homographies, you can get cross-sectional lines that go from one image to the other image to the corresponding points. So if you have this point X in space, it projects to the center of one camera and also projects to the center of the other camera. These two camera centers can be joined by a line that goes through something called an epipole. So figuring out the epipole comes from decomposing the homography from one image to the other image. So once you've figured out an epipole and you have a homography, you can get a fundamental matrix which describes the way that these lines are drawn from epipoles to the projections of the point in space. And from that, if you have two calibrated cameras, so the K and K prime are the intrinsic matrices of both of the cameras, you can then get the essential matrix. And the essential matrix is the exact, so basically if you take a point and you multiply by essential matrix, you'll get a line in the other image where that point is going to be. So, and the essential matrix can be decomposed into the rotation and translation of one view to the next view. And this decomposition will actually be in meters in angles. So using this technique, we figured out our rotation and translation between the two cameras. So through camera calibration, we've calibrated the RGB camera to have these focal lengths and these principal point and the depth camera down here. And the way you can see that this makes sense is that this principal point should be about in the center of the image. It's not always in the center because the aspect ratio is different. And the depth, you can also see that the focal length of the depth camera is shorter.
Units is in pixels?
Yeah, these are pixels. So you can see the depth of the focal length of the depth camera is shorter, meaning it has a different field of view from the RGB camera. So over here is the rotation and translation matrix that we got for this sensor, and you can see that the rotation matrix values are all very small. That's because the two cameras are facing in the same direction. And the translation matrix over here, so this is translation in X, this is translation in Y, this is Z. So you can see that Y is very small because they're also on the same axis. And you can see that they're separated by about 2 centimeters in the X direction, which is actually true if you look at it. And 1 centimeter in the Z direction. And that's actually interesting because remember when I talked about the camera center? The camera center is a virtual concept, sort of. It's like there is no actual camera center. It's where the lens focuses. So you can see because these focal lengths are different, you actually have a disparity between the two camera centers. So knowing the rotation and translation, we can take a point in one image and modify it and figure out the corresponding point in the other image. And even though supposedly, well actually, so once you do get it, what it looks like is the points in the depth image perfectly, or almost perfectly align with the points in the RGB image. So even though stereo calibration is supposed to give us better results, I didn't actually see that. With stereo calibration, I got the two images were off of each other, an average of about 1 pixel. With the other one was an average of about 0.8 pixels. But I don't consider that one better, it's just happened. When in the uncalibrated case, you have about 30 pixel separation between two images. So the deviation is also similar in both methods. So I guess if we had a much higher resolution camera, we would see a much better result from stereo calibration, but in the case of basically webcam quality, we see the same result. So either method is okay to use, but this one's much easier.
Is there a reason why the center disparity is so high for the uncalibrated?
Yeah, because they're the two cameras are in two different places. So what we're trying to do is put them in the same place mathematically.
But you're talking about a disparity of 1 pixel
1 pixel
between these two algorithms.
What's that?
The difference between these two algorithms is fairly small.
Right.
I mean, really small.
In this case, it will be bigger if the resolution was higher. Because if the resolution was higher, we would get a better calibration for using stereo.
Yeah, you get more pixels.
Yeah.
Or if the distances were higher, you're dealing with images far away.
Right. So 1 pixel with a faraway image could be actually have a big difference. So something.
So it's really a percentage. What you're talking about here is a percentage.
You mean for these values?
Yeah, I mean, so it looks to me like if the uncalibrated distance is 30 pixels, you're off by like 0.5% or 1/3%.
For the uncalibrated?
Either of these techniques are off by about 1/3%. Right. Which is not too bad. I mean,
No, it's practical. Both of these are great.
and the differences between them is on the order of half of that. We're talking about,
I don't even really see this as a difference between them because for another 300 points, it might be the reverse. So.
Okay.
But so these.
Now I got to ask my question.
Go ahead.
You just dropped. Are these differences statistically significant? you let me. I wasn't going to go there, but.
I have a histogram later.
Okay, well, we'll come back to that issue. I suspect they aren't.
Well, in the case of the low resolution camera, they're not. But if the distances were higher in this high resolution camera, we'd see different results.
The same way they explain. Sorry to interrupt.
Yeah, you already have your PhD, so you're not allowed to defend them.
What's the advantage?
These two will
Right,
method over
right.
the other.
Right.
Well, numerically there is no advantage in either one, but this one's just easier because with this one you need to calibrate both cameras. You need to take multiple snapshots. With that one, you take only one snapshot. Which, in a case where you have a high resolution camera and a lot of space, that one snapshot is not going to give you a good representation of the space. Where with this, you would have like complete correspondence between two cameras. So this might work in a small scale, but in a big scale, it's going to be wrong. But in our application, both methods work. But yeah, so once we have corresponding pixels in both the RGB and depth image, we have to translate them into meters. So experimentally, some people, this is from people at Blue Garage that I got this graph, but experimentally it was figured out that the depth falls off linearly because the Kinect doesn't actually give you depth in meters, it gives you depth from 0 to 2048 in just integer numbers. So using this equation, since the depth falls off linearly, you can basically plug in that integer number and figure out the depth in meters. So once we get a point in the RGB image, we can take the corresponding point and figure out how many meters it is far away. And this actually is pretty cool. So like, since projective geometry is linear, when you have a point and you know its depth, you can, and you know its x and y position in the camera image, its x and y position in meters in real space is going to be proportional to that. So you can easily figure out the x and y positions of the projected corners using just projection. So over here, for example, we've projected a calibration pattern on the wall, and it's about 2 meters away that this projection was done. And since we have a calibrated camera, we know the focal distance is here. We can take this depth and the pixel location and get back our centimeter or meter values over here. So the second point is actually 8.2 centimeters away from the first point. And we can check that by measuring it. So over there I got about 3.2 inches, which is 8.2 centimeters.
You see it's 2 meters. Sorry, showing it.
Yeah, it's 2 meters, and this point is about 8 centimeters away from this point, and in the x direction, and it's a very short distance away in the y direction. So basically, using that, we can figure out the 3D location of each point of the projected pattern. So because now we basically have known the pixel locations of the points and exactly where they're being projected out in 3D space. So now you have these points and the 3D points, and you can get back the projective matrix. So essentially, that's the result of what we want our calibration or what these methods to do is get back our 3D points. With the other method, the way this works is since you don't use a depth sensor, you actually have to physically take a big panel and stick a calibration pattern on it, a physical calibration pattern that's known. So we have to know how big the squares are in a physical calibration pattern in meters. So when you have this glued to the pattern, you know that these are like 30 millimeters. So the camera would then see this big plane with the calibration pattern on it, and knowing what this calibration pattern actually looks like, you can then recover the normal vector of the way that this plane is oriented from the rotation, from the extrinsic parameters, and then you can also figure out the translation with respect to the camera center using the extrinsic parameters. So from that, you have the normal vector and the translations. You can then get the equation of the plane with known A, B, and C, and D, which when you take an X, Y, Z point, place it on that plane, you can figure out its actual location on that plane. So the way this works is, like I said, since you can take a 3D point using an inverse projection matrix, which we know from the camera, and we can then recover then we can recover the 3D points over here. But since it's a camera, not a depth sensor, we can just recover the rays or the directions that these points are oriented with respect to the lens of the camera. So, and these rays, if you scale them by some factor, they're going to terminate at that plane. So when you take this and you take those rays and you plug them into this plane equation, since A, B, C, and D are known, and Rx, Ry, and Rz are known, you can figure out the exact scale or point where this ray V will terminate on this board, and I can actually get the X, Y, and Z location of each point the same way that we did with the RGBD sensor. So now that we have these points, X, Y, Z points, and X, Y points in the projector, we need to figure out the projector matrix, which is the goal of this entire thing, is to figure out the intrinsic parameters of the projector. And what this projection matrix actually does, when you capture a scene, the scene is captured with some raw information, like I said, with those depths of 0 to 2048. And using the correct projection matrix, you can get the way that that scene would be prospectively projected onto the screen. So, what was I going to say? So depending on the projection matrix, you can have something that looks like this strong perspective over here and this weak perspective over here. And applying that to the captured points, you basically get what the captured information looks like through the camera, but from the projector. So what that would be doing is, like I said, both camera and projector have a cone, but there might be longer cones and shorter cones. What the projection matrix would do is match that size of those cones. You know. So now you have these two-dimensional points in the image, the projector's image, and you have the three-dimensional points where the projector is projecting out that image. You can start to get this P projector matrix. So you need at least 6 points, since this is a 3x4 matrix. So since x points, so if small x, which are the pixel points, and big X, which are the 3D points, if they're known, you can then create 12 equations for those 6 points to try to figure out these unknown P parameters. So once you have these P parameters, they're actually undefined due to scale, since the projector again projects rays. So the way to figure out the final scalar parameter is through minimization. So when you take the projected points with an instance of projector matrix and subtract them from the actual 2D points, which are known, you can then, through minimization, get this final P matrix. So, and at this point, we're still not done, because this P matrix is a composition of the rotation and translation parameters also included into it. So this is basically intrinsics multiplied by the extrinsics. So the first 3x3 is actually the intrinsic matrix multiplied by the rotation, and the last over here is just the translation. So in this case, we're not interested in this because this is just the projective patterns extrinsics in relation to the projector. We're more interested in getting this K matrix, which will give us the right perspective. So since this is an upper triangular matrix, you can use something called QR decomposition to recover the K matrix from this matrix of rotations and intrinsics. So now you have this K matrix. So this is some of the K matrices that I've got for different projectors, and you can see that using different Ks, the scene looks a little bit different in each of these. So for example, in this case where the focal distance in X is shorter, then you have this aspect ratio where the image looks a little bit stretched out. So same thing in this case where the focal distance in Y is shorter, the image is stretched out a different way. And this one is about even. So depending on the projector, the resolution of the projector, and the aspect ratio, you would have different projection matrices. So our goal now is to take this scene and properly position it in a way that it's projected out from the actual projector. So since the sensor captures the scene from one angle, since they're separated, and the projector projects it out from a different angle, we need to take the scene that the sensor captures and rotate it to be as if the sensor is projecting it out from the projector. So this is very similar to what I did with stereo calibration, with trying to figure out how those two cameras match. And what we need to figure out is the rotation and translation physically between the camera lens and the projector's lens. But it becomes a little bit more difficult because the projector is not a camera and it works in reverse. So, but in this case, since we already figured out, we've already calibrated the projector, we know the intrinsic matrix for the projector, and we have a calibrated sensor or camera, we can then take our two intrinsic matrices and the fundamental matrix and figure out our central matrix, which is just a cross product of this R and T's. So then getting an R and T, you get the physical relationship of the camera to the projector. So over here, this is an R and T for something that looks like that, and the Kinect is on top of the projector. So you can see that the angle in Y is separated by about 3 degrees in that case, and then this was 1 degree into the left, and the angle was really an issue. And then also here, this is translation in X, Y, and Z. So we can see the X and Y. So here, this is probably 1 centimeter off of the center of the top of the projector, and the translation, so this is about 12 centimeters up. So knowing this rotation and translation, we can then take that scene that we've captured and rotate it. So, and how do we do that is we use OpenGL. So OpenGL is really great because it gives you a way to simulate a camera within its kind of 3D environment. So the way OpenGL does that, it has these functions. It's really simple to use. We just give it arguments of field of view, aspect ratio, and the near and far plane, and also the center of the image for how it's positioned. And you basically get this camera frustum that, with this being the front of the screen and this being like the back of the projection. So having our R's and T's in the intrinsic matrix, we can then decompose them to figure out what these parameters are for these functions. Because basically what it does is just take and simulate intrinsic and extrinsic matrices within this software. So you have this matrix pipeline that does it with. So you have this model view matrix, which handles rotations and translations, and you have the projection matrix, which handles the perspective. So when we capture a scene, it looks sort of like that. And then using the model view matrix, according to our rotations and translations, we can take the scene and rotate it properly. And then using the projection matrix, we can make it look as if we can make it look proper in the projection screen. And finally, when we project it back out, the image should fall on top of the captured image. So now that we can do that, we can project image on top of what we've captured. How do we really see how accurate this projection happens? So over here you can see these chessboards should match up with these corners. So what we do is we look at the reprojection error. So when we project out the calibration pattern back onto itself using the projection matrix, it would either be a bad calibration where it's off, or the good calibration where the corners match up and they're spot on. So when we project out, so over here, we project it in 2 different colors. So you can actually capture both calibration patterns at once. So over here, this dark black is projected in the image, and over here, this gray, it's actually red, is
Use the pointer.
it doesn't work.
It works on the top.
Oh. You told me that like an hour ago. Okay, so you can see that like in this picture, the corner doesn't perfectly match up to where you want it to be. And when you capture both of them, the points sort of misalign. So after getting the average of these points, and this is what I've gotten with my results. So this green point is the actual location of the calibration pattern where we want the projection to go. So this is actually like an average set of the points. So, and this is done for about 1,000 iterations with projecting it. These blue ones are using ray plate intersection, figuring out the depth by using a movable plane throughout the space. And these red points are done using the Kinect sensor. So you can see that like the center of this distribution, this X here, very close to this, and this one's actually further off. So my method actually had about a 3 pixel deviation from where we wanted to, or disparity from where we wanted it to go. And the popular method had about a 0.5 pixel. So, and also you can see that this is the distributions of the where the pixels were fell. So these two are using the array planner section, the popular method. So you can see the distribution is much more uniform. Like you can see that since they're all kind of centered around this mean, and you can see over here are just chunks. So you can see these chunks over here. So I had another video over here what the final result should look like. So the way I think I can explain that is because the depth camera is low resolution and there's a lot of noise, and we also use some filtering on top of it. So sometimes what happens is, even though we want the depth at this point, only get the depth of the point in the background. So, which I think is what would happen, because it might have, for a whole bunch of points, instead of getting the depth of this here, it got the depth of the background, and then placed the point in a different space. So maybe there was 3 different areas where that point could have fell. So, and that contributed to our worst result. But even though the result isn't as good, it's 3 pixel separation, which can actually have a big effect, especially if distances are high. So if you look at a camera and something 3 pixels separated, and it's 100 feet away, you know, it could be, the separation could be like 3 feet. So, but since the Kinect sensor only works in a space about as big as a room, these are more than acceptable for practical applications in a setting like a stage or a room. Maybe with a projection on a building, you wouldn't be able to use something like this. But in our application, especially with collaboration with the dance people and also just doing demos here, it works very well, since the main advantage of it is basically the fact that it can be deployed very quickly. You only need to project one pattern and capture it. Well, that's assuming cameras have been calibrated. And based on that pattern, you can get the rotation and translation between the projector and camera, and then get the depths. With the other method, you need to walk around with this plane, which might be cumbersome and more difficult to set up. So, and further, I want to look at some other calibration methods. These are just 2 that I mentioned. Another popular method which people have been doing, which as far as being easily deployed, is this calibration using structured light. In that case, they take patterns of lines and project them out on the space, and then see how these lines are bent. And based on that, they can tell the 3D geometry of the space. So another thing we want to do is take a lot of this and implement it in MATLAB, since all this is in C++. And with MATLAB, we'll be able to get some better analysis and be easier to look at the data. Then finally, want to improve the software that makes use of the projection matrix, because right now to get it into OpenGL, we have to hard code it. Anyway, so I have backup slides too. Any questions? I have a demo also.
Question, right? So it works like at different distances, right? Like,
Yeah.
Okay. So do you have like some type of recovery mode? Like if, for example, like it works at this distance and somehow you lose like the calibration? Like...
Right now, no. I guess. Actually, that's a good idea, because so one way to lose that calibration is if you move the Kinect. But the Kinect actually has accelerometers in it, so say if you detect movement in the sensor, you can then automatically recalibrate. That's cool. So I have this demo where I use Fourier transform. I knew that's the question depth Y would come in. So I just want to demonstrate accurate projection onto. So when I snap my fingers, I can get light projected directly where I want it to go. And you can see that it works throughout different depths of the space.
Nice job.
So I figured out what frequency I snap at.
I cannot do that. Hey.
Any questions? Not about for transferring this out of the scope of the project.
You thought about any sort of financial aspects of this program? I don't mean in terms of you getting money, but I mean in terms of selling it for something you could do.
Yeah, one idea, I had an idea where I wanted to, like, let's say a projector could be set up on top of a building and people are walking down the street, so you can project advertisements at their feet as they're walking by. Like live pop feds.
The other question is, what would be involved in doing this in 3D?
You
In other
mean,
words, so, yeah, I mean, because I was thinking about this. And the idea is that what you do is you have a plot of land and somebody wants to put a house on it, right? So what you do is you project the house onto the plot of land so they can see how it fits with the environment.
so actually, so like a hologram?
Yeah, but you could do it with the handheld device.
Oh yeah,
also,
so you can kind of see through it.
just something so you can just kind of.
I was thinking it could be possible to, have you ever seen those, like, sometimes on the internet you see people have drawn something with chalk on a sidewalk, and if you look at it from a certain angle, it looks like a big hole in the ground. So you can kind of project illusions that would look correct from a certain angle, maybe. So if everybody's standing, at some point, from that angle, it might look like there actually is a house. But a lot of that is 3D graphics and 3D programming, and I haven't really done too much of that yet.
My question is about the path for this 3D chipboard.
Oh yeah.
Does that matter how high of this black chessboard raised it up?
I haven't looked into that since you just need a difference in depth between the front checkerboard and the back.
You said if the
Oh, if it's flat, you can't see
right,
it.
you can't see it, right? So that would be pretty bad calculation. But if you raise higher, would the accuracy get better?
No, because all you have to do is just detect the chessboard pattern. It would be easier to. Well, that's not so much. Because to detect the chessboard, I used an algorithm that's available in OpenCV. Because the chessboard is what everybody uses. So figured it was the easiest because I could do all these different things as far as point transformations from a chessboard. It could mean that, of course, the calibration could change if you use a different calibration pattern. And that's another area. There's a lot of variables in this, I think. So, like, if you had a higher resolution 3D sensor, you could probably have a much less deviation from the center.
Is there any limit to the depth sensor as to how much depth it can?
Yeah, there is. It's about 5 meters.
5 meters.
Oh, you mean it works further, but at that point the noise becomes pretty high.
Any other questions? Not, let's give him a hand.
So for the benefit of the other graduate students in the room, I want to compliment Mike on his slides. This is probably the nicest set of slides for defense I've seen in my 2 years here, and many of my previous years as well. So you should take some notes on how he presented the material in a very easy and accessible and visual way, and had very good command during the presentation of the audience, and he was in control of the presentation. So very nice job, Mike.
Thank you.
Do you want to stay as committee or?
No, I'm not on the committee.
Okay. All right.
Okay, I gotta use electrical.
If you don't pass them, I'll be very upset.
Thanks, guys. Should I leave this video running for Dr. Kong to see the committee meeting?
I think